So what we'll do next is talk about Lewis acids and bases. So this is going to wrap up the acids and base section. And so the definition of a Lewis acid and base is different than that of the Bronsted-Lowry. So a Lewis acid is a substance that is going to accept an electron pair, whereas a Lewis base is a substance that's going to donate an electron pair. So the classic example, which is used in most of the textbooks, is usually it's an amine, I guess. So with a lone pair attacking a compound that's got an empty orbital of some type. So here we've drawn A and it's got an empty p orbital. So the base will come in and donate its electrons to that empty orbital to form a bond. And that's just the most basic definition there is. So a Lewis acid accepts an electron pair, a Lewis base donates an electron pair. So what we're going to do is we're going to go through what makes a Lewis acid, what makes a Lewis base, and then this section will be over. So to be a Lewis acid, there's basically one of three requirements that you could have. The first is, and this is probably the most classic example, is a vacant low energy orbital. So an orbital that's got no electrons in it and is low enough in energy that electrons can be donated to it. So the classic example is on the periodic table. Our friend, so carbon, nitrogen, oxygen, fluorine, our friend to the left of carbon. So boron, and right beneath it is aluminum as another example. Remember, they have got 3 valence electrons, so when you make a Lewis structure with them, they are an exception to the octet rule. They've got 3 bonds each, and they've got this empty p orbital. So I've answered the question here. They've got an empty p orbital, which is low in energy, and then any substance with a lone pair, say some sort of amine, can just donate its lone pair to that empty orbital to form a dative bond. So vacant low energy orbital. So this would be group 3A on periodic tables. I need to get a postable periodic table. Make sure you've got a periodic table. They're very maybe a pocket periodic table or something. So right beside carbon to the left, that's where you'll find so boron compounds, aluminum compounds, indium is down there too. So look up those. The next class would be just a metal cation or a transition metal. So lithium and magnesium, lithium plus magnesium 2 plus, what's the orbital that is empty, which is low in energy, which could be used there? Let me draw something. So we've got hydrogen, helium, lithium, beryllium, and then boron, there's a gap, sodium, magnesium. So the Yeah, so lithium would be using a empty 2s orbital. Magnesium, which is one row down, would be using an empty 3s orbital. So they've got empty s orbitals that they're using. Correct. Okay. Transition metals. So titanium, iron, zinc, all of these have got, what's the neat type of orbital that transition metals have? So in these cases, and you remember with transition metals, we tend not to, like, you take an inorganic chemistry class if you want to learn all of the fun stuff about transition metals. But there's one type of orbital which transition metals have that we never seem to talk about in class because carbon doesn't have a low energy, that type of orbital. And those would be d orbitals, right? Okay, so with these metal cations, used typically for things of lithium, magnesium, so we got s orbitals, empty s orbitals, and with the transition metals, we've got d orbitals. So if you ever had to draw and so when you've got transition metals, the octet rule doesn't apply. So so just keep that in mind. You can make multiple bonds to transition metals. Often there's 6 bonds to transition metals, so that the octet rule doesn't apply. So the most common one is titanium or iron. Zinc's another one which is used often. It depends upon what they're being matched with which heteroatom. Lithium and magnesium are often used to complex carbonyl compounds, so like ketones and aldehydes and that sort of stuff. But anyway, so metal cations or transition metals, that's the second class. So the first is like compounds like boron or aluminum. The second is transition metals. The third is what we've just seen before, a polar bond to hydrogen. So I said previously that that the Bronsted-Lowry definition is encapsulated in the Lewis acid-base definition. And so if you've got a polar bond to hydrogen, the basic reaction is that the Lewis base is going to remove that proton, and then the electron pair that the Lewis acid is accepting, it already actually had because it's in this bond, and now it's moving on to it. So what would we call the conjugate base? That's the Lewis acid after it's accepted that proton. So after it's accepted that lone pair. So the Lewis base is going to get protonated and form the conjugate acid. And the Lewis acid is going to be deprotonated and form what we would have called previously the conjugate base. So a polar bond to H, a polar bond to hydrogen. So basically everything which is in the Lewis acid, I mean the Bronsted-Lowry acids and bases. So we're just, previously we would just call this the base and this the acid, but now you can actually call this it's actually technically a Lewis acid because it's got a polar bond to H. So if we're now to be a Lewis base, this is really way simpler. The definition is that all you need to do is have a lone pair that can be donated to the Lewis acid. So most oxygen, nitrogen, sulfur containing organic compounds are Lewis bases. So here we've got like a tertiary amine, so a nitrogen which is bonded to 3 carbon atoms. It's got a lone pair, it donates that to the aluminum, and you form this bond, and now the nitrogen will have a positive charge and the aluminum will have a negative formal charge, because if we do the formal charges, aluminum used to have 3 valence electrons. Now it's got 1, 2, 3, 4 bonds. 3 minus 4 is -1. And so that's basically what's going on with these. So this is the classic example. If we did this in Gen Chem, that would have been it. So if you've got a nitrogen, oxygen, or sulfur containing organic compound, they've all got lone pairs. They can all donate them. So they can all potentially be Lewis bases. Now that depends on the very next question. Actually, no, I skipped ahead. Let's go to the next question. Can a substance be both a Lewis acid and a Lewis base? And the answer is absolutely yes. So if we look at water, and water is the best example, it depends what water is reacting with. So it can either use its lone pair and donate them to a Lewis acid, and in that case it would be a Lewis base, or if there was a stronger base which came along and grabbed this proton and it accepted these electrons, then it would be a Lewis acid because it's got a polar bond to H. So it depends upon what its partner is. It can be either, but specifically it will be one or the other based upon what it's reacting with. So that's, and we'll do an example of that in a second, but I'll go back to this, this previous slide. So with Bronsted-Lowry acids and bases, we had a scale which dictated what's the strongest acid, what's the strongest acid. And from that scale, we could derive what's the strongest base, because the strongest acids will have the weakest conjugate bases and the weakest acids would have the strongest conjugate bases. So, but there is no scale with regard to this in for Lewis acid and base strength. But there are certain Lewis acids or Lewis bases which would preferentially complex with each other. And the wonderful world of inorganic chemistry, this would be revealed. So what you would see if you take these courses is that there's a different definition. You can have a hard Lewis acid or a soft Lewis acid. You can have a hard Lewis base or a soft Lewis base. And so hard Lewis acids tend to complex with hard Lewis bases, and soft Lewis acids tend to complex with soft Lewis bases. One of the areas where you'll see this is actually if anyone's in geology, if you look at, say, like gold, silver, and copper, all of these metals tend to be found in sulfide-containing ores, whereas irons, these tend to be found in oxygen-containing ores. So you'd have like iron oxides, or you'd have copper sulfides, or so. And what's going on there is that iron is a hard Lewis acid, and the oxygen would be a hard Lewis base, and they're preferentially complexing with one another, whereas, say, gold is soft and the sulfides are soft. So it naturally forms these complexes, and that's how those ores develop. But that's basically outside the realm of our class. Just a tidbit of information. So there is no scale for Lewis acids and bases. There's more a hard, soft sort of stuff. So oxygens are hard, sulfides are soft. And the way we would look at that is oxygen is higher on the periodic table, sulfur is lower. So as you get down the periodic table, it tends to get softer and softer. All right. So let's try some questions here. Is this molecule a Lewis acid or a Lewis base, or neither? Or both?
Yeah.